introduction to backbone generation. So, like structure prediction, I want to ask, what is backbone generation? I'm sure you guys have ideas. Can you share some? Come on, it's not that hard.
Do you want the snarky answer? It's like generating a backbone?
There you go. Yeah, that's what I was looking for. It's not that hard. So really, the idea is you have a desired length of a protein you want, or maybe even some special conditions, and you want to just generate a realistic backbone that kind of satisfies those conditions, maybe a certain length, maybe binds a certain epitope, maybe has a specific topology. These are all things we can define with these backbone generation models. So you already probably have heard of many of the backbone generation models, but I want to talk about some of the generation metrics. So these are going to be some of the things that we use to kind of validate whether these designs are good or useful. So the first one of which is the self-consistency RMSD. The idea of this is you have a diffused backbone, maybe towards a specific target, maybe not, maybe it's just some unconditional generation. Then you take that backbone, you generate a sequence for it, for a variety of different ways you can do that, but maybe protein MPNN. And then you take that sequence and throw it through a structure prediction module, AlphaFold, ESMFold, etc. And then you check how well does that predicted structure match the diffused structure. You just simple RMSD alignment, and if it agrees, typically if it's less than 2 angstroms, people consider it a success. Otherwise, it's not a success. And generally, you want your self-consistency RMSD to be good.
It's considered good.
Less than 2 angstroms, usually. Of course, it depends on the protein, because larger proteins have more flexibility.
Is there methods for evaluation that doesn't require generating the sequence? Because how do you know the issues with the backbone that you generated the sequence?
That's a good question. Yeah, this isn't a perfect test, of course, because the sequence design method could be bad. The structure prediction module could be bad. The diffusion backbone could be bad. There's a lot of places for failure, but this is just one of the quickest, easiest ways we can do a check, and it's one of the most common ways. Okay. Another thing people look at is diversity. How diverse are the structures that you're getting out, the topologies that you're getting out of these generators? So it's really pretty simple the way to measure this. You just kind of, you just generate these structures, and then you do a structural clustering, structural alignment to kind of see how diverse they are. So there's fold-seek. You can do structural alignment, structural comparison with fold-seek. There's a variety of other ways. You can do multi-dimensional scaling to kind of reduce the dimensionality of these things and then compare it at that level too. So there's a variety of different ways people are doing this, but that's another metric people like to look at. Another one is the designability. This is pretty similar to the self-consistent RMSD because it uses it, but it's really the fraction of designs that have a self-consistency RMSD less than 2 angstroms. This threshold may vary depending on the method people are using. The literature is not very consistent with this. They also maybe sometimes use self-consistency TM score, which really is just aligning it and computing the TM score with that of the designed backbone with the predicted structure. But this is a useful metric to kind of like assess how good the backbones you're generating are for a specific sequence design method. It's like most people use protein MPNN or something like that. And another one, the last one I wanted to talk about is novelty. And the idea here is you're generating a bunch of backbones. You're curious how similar they are to the native PDB. So you just kind of do a structural alignment comparison between the generated structures and the PDB to see what the highest average TM score with PDB structures are. So this is kind of a measure of how well the model is generalizing to structures outside of its training set, which could be bad, could be good. But once again, we don't have great metrics for this. So if you have any ideas, we're always looking for better metrics for these because this is still a really early stage of the field, especially with these diffusion models, and we don't really know what works the best yet. But these are what we're currently using. Any questions? Yeah.
When you say under the designability column, fraction of designs, what do you mean by a set of designs?
So typically people would generate some backbones and then generate 8 sequences for those backbones, and then you would compare the fraction.
So you're saying in regards to those sequences that were defined from that topology?
Right, that backbone. Yep. Any other questions? 'cause I think this is pretty much the end. Oh, yeah.
So these metrics seem to only consider backbone or even just like three-dimensional space, but not the sequence.
Right.
Is there, or which I thought would be included in novelty?
Yeah. So part of the problem, part of what you're getting at is the fact that these models are just generating backbones. So it's kind of hard to say whether the sequence that we're associating with them coming from like language models is necessarily what that model would produce. Some of the methods now are coming up with joint diffusion methods, so they're coming up with ways to jointly sample backbone conformations as well as sequence. Those are a little more different, and you could totally do a novelty based on sequence or diversity based on sequence, but right now we're just talking about RF diffusion right now, so that's only backbone.
And do they, for these metrics, do they include the beta carbons?
No, it's strictly NC alpha and C and O. Yeah.
Can you comment more on or explain more the diversity column? So like, let's say we're doing a test generation of designing multiple binders to a target.
Mm-hmm.
How would we measure the criterion for diversity?
Yeah, so I think people typically use diversity in the sense of unconditional generation. So like generating without any specific target or any other conditional information. And so in that sense, the model's just creating things that it likes. So in that sense, you're kind of just creating a bunch of designs and then clustering them and seeing. I don't know if that answered your question, but
that gives me an idea.
Yeah.
I mean, with binder design, what I do is kind of something similar. Like
Okay.
I do clustering, but I also measure by fraction of secondary structure for a given sequence.
Okay.
Or that would be backbone.
Yeah.
Yeah.
So to make sure it's not like overly loopy.
Overly loopy or just a long single-stranded helix, like a Rosetta diffusion.
Yep.
Kind of like.
It does happen. Yeah.
Sorry, this question was already answered but diversity seems like an extremely subjective parameter. So like the number of clusters is not really.
Yeah, I agree.
How do you?
It's also not the only way people measure diversity. So like, I agree, it's problematic, and a lot of the papers are also inconsistent about how they define diversity or even designability or novelty. So I don't think it's something that the field has settled on, like what the best metric is for these, but these are just some of the common ways people are using to evaluate some of the generations that these models are creating. They are imperfect, I totally agree. And they can be subjective. And a lot of these depend also on the sequence design method that you're using. So if your sequence design method is really bad, maybe it's Rosetta, which is a few years old at this point, versus like Protein MPNN or something like that, or even like newer versions of that. It really depends a lot. Anything?
Are there like does Rosetta RF diffusion or like other tools that can they provide these metrics inside? Or?
You kind of just calculate it by hand. You generate a bunch of things, and then you write a script to say, cluster these or generate sequences for them and then refold them. So yeah, there's not like a nice evaluation toolkit people can use. That is something that the community really desperately needs.
It would be nice for standardization, right?
It would be really nice for standardization and benchmarking, not just for backbone generation methods, but also sequence design methods, structure prediction methods, etc. We really desperately need a standardized benchmarking platform or something like that. Okay, why would we use backbone generation? Well, you're going to be using it for the binder design project. So you're going to be given a target protein, which you already have, and then there's also an epitope that's in the activity. There's a little table at the end that specifies the hotspot residues that you'll be using for your binder design project. And the idea is you just design a binder towards it. There's also active site scaffolding, so you can hold a specific set of specific residues fixed and then generate a scaffold around it to harbor that active site. You can also do motif scaffolding, which is quite similar. You have a very specific motif or a partial substructure of a protein that you're interested in. Maybe it's like, I don't know, a very specific loopy, or I don't know. You can do stuff with that. I can't think of an example right now, I apologize. But the idea is you just have that motif, you keep it fixed, and then you generate the rest of the protein around it such that it actually can harbor that site. And then you can also do symmetric design. So given a specific symmetry group that you're interested, maybe cyclic group 4, so you'd have 4 proteins in a cyclic arrangement, you can generate a structure given that symmetry. And the way they do that is really just diffusing a structure and then copying it over based on that symmetry group. And there's a variety of different symmetry groups like dihedral symmetry, tetrahedral symmetry, isocosahedral symmetry, yeah. And we'll be playing around with some of those in the activity. Now this should be the end of it. Okay, cool. Let's talk about RF diffusion.